Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This would be video 2B. It'll be part of the Why series, and we're going to be talking about here why we need to get the net zero greenhouse gas emissions, and this is going to be part 2. And this is also going to be a part of our foundational core video set. So why net zero greenhouse gases? Well, in the part 1, we talked about why we need to get the net zero greenhouse gases. And if you take a look at the thumbnail in the lower right-hand corner, you can see the thumbnail for video 2A, part 1. And if you haven't looked at that, I would suggest you maybe stop this video now and look at that first. Now, in this video, we're going to continue our discussion of some of the basic, I guess I would say, criticisms or comments, etc., that I received from climate skeptics. And in part 1, we addressed this statement that there are credible experts who are skeptical, and I believe an open and honest dialogue should be allowed to take place as science is never settled. And I would agree with a lot of those statements. One, science is, of course, never settled. And I'm always in favor of an open and honest dialogue. But implicit in that question is an assumption that there is significant disagreement among climate scientists about the underlying science that deals with greenhouse gases, etc. And it just isn't any. And we talked about that in 2A. Okay, so in this section, I'm going to talk about this other second major comment, and that is the Earth's climate's always changing, and the current climate is just part of the normal change cycle. And yes, true, climate is always changing, of course, okay? But the real question is it really part of the normal change cycle, or is there something really extraordinarily different going on right now? And we'll address that in this video. And in part 2, we're also going to focus on the science and what's going on here. But the focus now will be on how greenhouse gases actually are impacting Earth's temperatures. And we'll talk some more about that. So let's begin. So I would want to really begin with addressing question 2. But as my client buddies are suggesting here, before I begin question 2, they really have one question they want me to answer, and that is there any proof that temperatures are actually rising? And I think that's really a great question. So I say, yeah, let me show you. So what you see here is a graph of actual global temperatures. And this graph happens to go from 1940 up to the present. And you can take a look at the white bars there and dots, and you can see that clearly there is an upward trend occurring. You know, recently we've had a couple of down years, but those are really the COVID years that heavily influenced this. So you can see it's gone up very dramatically. If you take a look at the arrow, you can see in the last 10 years, from 2014 to 2024, temperatures have gone up from 14.6 Celsius to 15.1 Celsius, or half a degree Celsius. Since most of us live in America and we can't relate to Celsius, I thought I would also translate that to Fahrenheit. So currently, this was as of December, the temperature was 59.2 degrees Fahrenheit. 10 years ago, it was 58.3 degrees Fahrenheit, or we basically have had 0.9 of a degree increase in average temperature in the last 10 years. So yes, temperatures are increasing. Number 2, this is an interesting point. It just so happens by coincidence that 15.1 degrees Celsius actually equals 1.5 degrees Celsius from pre-industrial revolution, because a lot of the literature you see, if you do searches, they all talk about 1.5 degrees Celsius, 2 degrees Celsius, 3 degrees Celsius, etc. And all of those are from pre-industrial levels. Well, it just so turns out that at the end of the year, 15.1 degrees is exactly equal to 1.5 degrees Celsius. And it's kind of important. Because look at point 3. All the countries got together in 2014. They actually signed the accord in 2016. It's called the Paris Climate Accords. And they set a target. And that target said, first of all, we don't want to reach 1.5 degrees Celsius. But if we do, we want to make sure we don't get there until at least 2050. And then they set a maximum target saying we never want to get above 2 degrees Celsius. But if we do, we surely don't want to get there before the year 2100 because the consequences are just so significant. Now, if that accord was signed in 2016, that probably says that for sure the scientific data at least probably dealt with the latest could have dealt with was 2014. So in 2014 we're doing this. They didn't want to see temperatures increase to 1.5 degrees Celsius until 2050. And what's happened? We've done that in 10 years. And so we don't want to hit 2 degrees Celsius until the year 2100. Well, the difference between 1.5 and 1 degrees and 2 degrees Celsius is just a half a degree Celsius, right? Well, we did that in the last 10 years. So if we keep at that pace, that says we'd probably be there about 2034, not 2100. So let's continue. So next question, you're saying, well, yeah, but a lot of people tell you, well, but I get messages all the time. It says, well, here, look at the temperature in this city was X, and look back in 1882, the temperature was lower, that was higher than that, so we're not at the highest temperature, etc. Let me tell you how we calculate, how average surface temperature is calculated. It's not taken at one point in time. It's taken around the globe, and it's taken over the ocean, and it's taken over land, and it's also taken over in the Arctic. If you can see this chart here, from 1900 to 2020, you can see that over the ocean, temperatures are rising. You can see that's the blue line. You can see the red line for land. They're rising faster than they are over the ocean. And they're really rising very fast in the Arctic. Now, that's really significant, but we'll talk about that in other presentations. But the reason I want to show you this is to just illustrate and just make the point that when we're talking about average temperatures, it's a very comprehensive average temperature. Okay, so now I'm ready to begin question 2, but again, my golf buddies have one more question they want me to address. Is there any evidence that greenhouse gases are causing temperatures to rise? Again, that's an excellent question. So let me try to address that quickly. So take a look at this chart in the upper left-hand corner and look at the yellow line. And now look at the axis, the yellow axis there, where it talks about carbon dioxide. That's a line of carbon dioxide. And look at the amount of parts per billion that we're talking about. In 1880, we were under 300 parts per billion of carbon dioxide in the atmosphere. Today, we're over 400. In fact, I think the last number I saw was around 430 parts per million. Now, the other thing they've done is they've charted temperature. That's the blue line. And we've seen evidence of that. It looks sort of like the graph we just talked about a couple seconds ago. And you see it's highly, highly correlated to what's happening with regard to carbon dioxide. Now, does that make sense? Well, if you watched part 1, this is exactly what one would have expected to happen if one just looked at and understood the quantum mechanics rather of greenhouse gases and how they interact with the long wave radiation of the sun's light as it's radiating back from the Earth's surfaces. That's exactly what you would expect to see. That's exactly what the climate scientists are telling us is happening. So there is your evidence, okay? So now let me get on to addressing question 2. And that question is, we know the Earth's climate is always changing, and the increase in greenhouse gases and temperature are just part of Earth's normal cycle, right? And the answer again is no, it's just not true. Let me explain again. Okay, take a look at this graph, an illustration in the upper left-hand corner. Notice the axis. This measured carbon dioxide over the last 800,000 years. Now, we can't relate the numbers like that, so let me put it this way. You know, Jesus was born 2,000 years ago. Just think of what's happened since then. We're talking about 800,000 years. Now, look at, they've tracked carbon dioxide particles. What does it look like? You sort of see what looks like they call ice age cycles here. It's like it goes down, it sort of hits the bottom just below 200 parts per million. It gets pretty close to just below 300 parts per billion over this period of time. And it sort of goes up and down, right? And it seems like a sort of natural kinds of cycles. And then look at just what happens recently. And it's probably, you can see on this chart, when I get the zero, it just goes straight on up, right? Just straight up. We're clearly outside of any normal historical range for the last 800,000 years. And if you want to suggest that there's some other range before 800,000 years, let's get real, okay? 800,000 years, you know, given our lifespan and everything else, it's really probably a pretty credible range to talk about. If you take a look at that and it tracks it from the Industrial Revolution, look what happens as the Industrial Revolution starts. The amount of carbon dioxide particles are going up dramatically in the atmosphere, right? So, as I said before, the historical ice range is somewhere between 2 to 300,000, 2 to 300 million parts per million, I should say, and we're currently at about 430. One other fact, you know, since the Industrial Revolution, they've determined that we've put about 1.8 trillion tons from using fossil fuels of carbon dioxide in the atmosphere. And then approximately 1.1 trillion tons of that has accumulated so far in our atmosphere. And we'll talk about that a little bit later on, why that's happening. So let's get to the next point here, point 4. Yeah, as I said before, climate cycles, the scientists will always say, well, the sun is a major driver, which it is, and temperatures are always changing. You can take a look at those cycles, you can see that it has been changing, and it's true. Over the historical ice age cycles, you know, what's happening in this ice age cycle? Why do we have this up and down? Well, it turns out that can be explained. There's a scientist called Milankovitch, and it's called the Milankovitch Cycles after him and his team. And they've really discovered what's causing that. And they came up with 3 major causes. And one they call eccentricity. And what does that mean? And what it means the change of the Earth's orbit changes, and it goes through a cycle. And the cycle takes roughly about 100,000 years. And sometimes the Earth is closer to the sun, and other times it's a little bit further away. And then there's a second factor, and they call it obliquity. And that's a change in the Earth's tilt. As you can see from the second thing there, that the Earth's tilt doesn't stay the same, it changes. It sort of goes in a pattern, and it goes through this pattern approximately every 41,000 years. And there's this last cycle called precession. And this is a shift in the orientation of Earth's rotation. And again, precession sort of has its own cycle with it, and it sort of repeats itself about every 26,000 years. If you take all of those factors together, that pretty much explains then what we've seen in these historical ice age cycles. So my question is, okay, do you understand why the increase in greenhouse gases and temperatures are not a part of Earth's normal change cycle? And you say, well, give me a second to think about that. And I say, that's great. But while you're thinking about it, can you check just one other thing? What's your mental posture? Is it closed, open, or somewhere in between? Well, let me say, if you're watching this video, you're not closed, okay? You may not be completely open, but you're probably somewhere in between that. But are you closer to closed or closer to open? I mean, where would you put yourself? So as we're going through the rest of this video, think about that a little bit, okay? And while you're contemplating that, let me tell you the rest of the story, because there's more to this story, okay? Another major factor causing carbon dioxide to increase is world population. Look at the chart on the right. And that shows you the world's population from 1834 to what it's projected to be in 2050. And if you look at the carbon dioxide and temperature graph, gee, there's a lot of similarities there, right? Yeah. Well, let me make one other point. Yeah, I think I graduated from high school around 1960. At that time, there were basically 3 billion people on Earth. In 2024, we passed 8 billion people on Earth, and we're projected to go to 9.7 billion people on Earth in 2050. Now, each human has some carbon footprint associated, right? I mean, we eat things, we have transportation of one sort or another, etc. I mean, so there's an additional thing going on that we need to pay attention to. So what does that mean? Well, one of the things it's telling you is that, gee, if we're going to have more people on Earth, we need to sort of reduce the carbon footprint for each person, right? Just to stay even. And we need to get much below even, because right now we're emitting significantly more greenhouse gases to the atmosphere than we're taking out. So we've got to do something to even those equations. And the fact we're adding more people to the world is just going to make it more difficult. So we need to take that into consideration as we try to figure out what we're going to do about this. I just want to make one other point. So far, most of the graphs I've shown have carbon dioxide, and probably some skeptics are saying, well, yeah, but that's just carbon dioxide. What about these other ones? Well, I use carbon dioxide because that's the only one we really went back and measured. And we have records going back 800,000 years on that. So how did they do that? They did it by ice core samples. Now, what about the other greenhouse gases? Well, take a look at these graphs once. Okay, look at temperature. It's going from the lower left to the upper right, right? Look at carbon dioxide. Looks exactly the same, right? Well, methane. We really started measuring methane about 1984. But it looks sort of like the same, like carbon dioxide does, right? And then we have nitrous oxide. We didn't even start measuring that to 2001. And look at that, that's even steeper than carbon dioxide and methane. So we need to pay attention to all of the greenhouse gases. And they're all moving in the same direction. They have the same message. It doesn't matter which one you're talking about. It's moving sharply upward from the lower left to the upper right. Now, here's some other really, really important characteristics associated with greenhouse gases. So I've created this table to sort of summarize that for the three major greenhouse gases. And so we're going to talk about the type of gases, what are the sources, what are their sources, what percentage do they represent in the atmosphere. We're going to talk about greenhouse warming potential, and we're going to talk about atmospheric life, or how long does it stay in the atmosphere. So let's start with carbon dioxide. Where do we get carbon dioxide from? There's a lot of things, but primary reasons are fossil fuels, deforestation, transportation, producing things like steel, cement, plastic, etc. It represents 76% of the greenhouse gases in our atmosphere. And it has a greenhouse warming potential of 1, and it hangs around in the atmosphere. This is kind of frightening. From a few months to 400,000 years. So remember back when we said we could choose 1.8 trillion and 1.1 trillion tons is still in the atmosphere? Here's why. Once it gets up there, it hangs around for a long time. Now, why does it have a warming potential of 1? Well, because it was the largest greenhouse gas. Scientists just arbitrarily assigned it a potential of 1 and then measure everything else off of that. So let's go to the second line, methane. Where do we get methane from? Well, from agriculture, from farm animals, etc., growing things. Natural gas, landfill, permafrost thaw, etc. And it represents 16% of the greenhouse gases. But it has a warming potential of 28 times. So it's 28 times more potent than carbon dioxide. And it stays in the atmosphere for 7 to 12 years. That's actually pretty good for us. Because that tells us if we can really do something about reducing carbon dioxide, we can flush that out of our environment pretty quickly. And we can see an impact from that. Whereas if you reduce carbon dioxide, you're not getting rid of the old stuff for a long time. Let's get to nitrous oxide. Where's that come? Well, from fertilizer, biomass, combustion, industrial processes, etc. And currently that's 6% of the greenhouse gases in our atmosphere. But it has a GWP of 265 times. It's really potent. So we really need to pay attention to this. And the other frightening thing is it lasts in the atmosphere over 100 years. So let's continue. So my question is do you understand why increasing greenhouse gases in the atmosphere and the corresponding increase in average surface temperature are not just part of Earth's normal change cycle? Do you get it? Do you get that what's happening now is abnormal and we need to deal with it? And while you're thinking about that, let me just make a prediction of how my golf buddies are going to respond to this. And I think the response is probably, interestingly enough, it's going to depend more on their mental posture than it really is on the scientific evidence. Are they closed, or how closed are they? Are they open? How open are they? I think that's true of just about everybody. Because the scientific evidence, quite frankly, is pretty strong. So let me get to this slide. And this is really, really, really important. I call it the bathtub effect. And what that's saying, it is the level of greenhouse gases. Now, technically, it is the sum of the GWP, of the greenhouse warming potential of those greenhouse gases in the atmosphere that influences global average surface temperatures. So what that's saying is the only way to prevent temperatures in the future from increasing is to reduce our greenhouse gas emissions to net zero. The only way. Let me use this bathtub as an example. Think of it, so we got water coming in. You got a bathtub, it has sort of a level, we got a drain. And so if the drain, the amount of water going out the drain is sort of equal to the amount of water coming in, the levels will sort of stay the same, right? If more water is coming in than it's going out the drain, the water level will rise, and correspondingly, if you go the other way. So now let's relate that to greenhouse gases. We know that we're putting a ton of greenhouse gases into the bathtub. And we know right now less is coming out of the drain. Now, historically, if it's say average over these ice age cycles, historically what happened is that we over the period of that, sort of the amount of greenhouse gases coming in was sort of equal to what was coming out, and so we sort of bounced around this range. Obviously, you saw the graph. That's not what's happening right now. So what's happening is our level of greenhouse gases is going up, just like the level of water in the bathtub is going up. What does that mean? That means that next year, next month, etc., the year after that, the year after that, the year after that, that water level is going to keep on rising. And so I'm doing this video towards the end of 2025. That means 2025 is the best weather conditions, temperature, Earth is probably going to experience in a long, long time. What your kids, what your grandkids, and their kids, and their grandkids are going to experience is going to be infinitely worse. Why? Because we're continuing to rise, let the level of greenhouse gases rise. We're letting the water level go up, and it's going up every single year. Do you get it? Think about that. The only way to prevent temperatures from increasing in the future and all the implications that has, like more intense hurricanes, droughts, etc., and I'll talk about all of that in other videos, is to get to net zero greenhouse gases. And it doesn't matter how much we put in, as long as what we're putting in, we're taking out. So if everybody wants to drive around in a gas-guzzling thing that emits all kind of emissions, that's okay. Just make sure we're pulling enough out to make up for that and to make up for population growth. Because what's important is we need to get to zero. So let's wrap this up. Okay, so in part one, we talked about the major components of greenhouse gases, how Earth, the atmosphere works, greenhouse gases work, what they are, the greenhouse effect, how the quantum mechanics of greenhouse gases interacts with the radiant heat from the sun, from the Earth, which came from the sun in the first place. We talked about the Goldilocks effect, and we talked about carbon cycles, and in this one we showed you the evidence that, yes, temperatures are increasing. We showed you the direct link to greenhouse gases. We talked about how this isn't a normal cycle and how the Milankovitch cycles sort of explain a lot of the historical changes we've seen in carbon dioxide and temperatures on Earth. We talked about the greenhouse warming power of each greenhouse gas in its atmospheric life, and they're different, okay, and it makes a difference. And we talked about the bathtub effect. If you haven't already, I showed thumbnails for part 2A and 3 in the lower right-hand corner. Hopefully you've already looked at 2A. You absolutely must look at video 3. Why now? And let me just say, wrap up with a few quick things here. And if you want, you just need to do something, okay? And one of the things you need to do is just vote, folks. Because our current politicians of both parties are just not going to solve this problem. If I look at one party, I can't think of anybody, maybe there's one or two people, that even think this is an issue. And the other one is not a lot better. So we need to get new elected officials, every level of government, that think this is a serious problem and are willing to address it. And the other thing you can do is really important was just subscribe to this channel and give me your comments if you think there's additional things we want to do. And just let me encourage you to do something. And I'm sort of going through this very quick because I'm looking at the time, and I see once again I made this way too long, and I'm sorry about that. I'm trying. Hopefully I'll do better in the future, but maybe based on my current track record, I won't, but I'm going to try. So thank you very much for spending some time on this, and have a great day.